All right, this section is going to go over stability with first order systems. So let's consider the system x dot is equal to ax plus bu with an output y is equal to cx. We can get a transfer function for this as well. Y over u is going to be bc over as minus a in this case. So how can we determine internal stability and BIBO stability? Well, for internal stability, we're going to assume zero input. We're going to be looking for the free response. So let's use the state space model for this. And importantly to note, we need to know there are no inputs that we're looking at here. So we're essentially looking at x dot is equal to ax, or x is equal to our initial condition times exponential of at. How can this system be stable? So what makes it stable? It's stable if a is negative, right? So the variable a is called the eigenvalue. It's usually represented by a lambda. And the inverse of the eigenvalue is something called our time constant, often represented by a tau. And the time constant is equal to tau, which is equal to the negative of 1 over lambda if lambda is negative itself. So when t is equal to tau, when our time is equal to the time constant, our state should have decayed to 37% of its original initial condition value. And we'll go over the definition of eigenvalue in a bit. Now, similarly for BIBO stability, we're concerned with stability, but it's for the input versus the output. So we're going to look at the transfer function in this case. Remember how that transfer function relates to the impulse response in the convolution integral. That's something to keep in mind. So what it means is that the denominator of the transfer function determines BIBO stability. If the output is stable with respect to a unit impulse, it's BIBO stable. So we just need to look at the roots of the denominator. These are the poles.